guys, welcome back to another Physics in the Flesh episode on dynamics, Carton on an incline. The carton shown below lies on a plane tilted at an angle theta equals 21.0 degrees to the horizontal with mu k equals 0.11. A. Determine the acceleration of the carton as it slides down the plane. And B. If the carton starts from rest 9.25 meters up the plane from its base, what will be the carton's speed when it reaches the bottom of the incline? So this is actually very similar to videos 69 and 68. In 68, we had something on an incline where it was undergoing static friction, so it wasn't moving. In video 69, we had a box being pushed down an incline, undergoing acceleration. This box is not being pushed, it's sliding down, okay? So it's still accelerating, right? Because it is, after all, gaining speed if it starts from rest, but there's a few less forces acting on it. So we're given this picture in the problem. First thing I'm going to do is draw my free body diagram. So there's a mass to this carton, and therefore there's a force of gravity acting on it, which goes straight down from the center of that object towards, of course, the center of the Earth. So we draw that going straight down. It's on a surface, so the normal force is going to be going up and perpendicular, okay, to that surface. And because it's sliding down, there's no push force forward, but there is a kinetic friction force opposing its motion, trying to slow it down. So FFK is going back. Now, similar to videos 68 and 69, because we have these two forces perpendicular to each other, FG is now the one in the weird direction. So I'm going to define a new coordinate system where X is down the incline and Y is up, perpendicular to the incline. Now, again, similar to previous videos, now that FG is no longer in one of the X or Y directions, I want to break it up into components. So I'm going to drop a vertical down, opposite direction to the normal force, and then I'm going to connect it with a horizontal component in the X direction. So this line right here, that's going to represent FGX, and this line right there, that's going to be FGY. And those two vectors, FGX and FGY, meet at a 90-degree angle. Now, this incline is at an angle theta right here. But similarly, using geometry, and as we've seen in other videos, we know that therefore that angle is the same too, the one right there inside this triangle, okay? So we'll see that later on, but that's theta as well. And we know that that angle is 21 degrees. So for part A, to determine the acceleration, okay, so we're going to use Newton's second law. Okay, so F net equals ma. Now, I want to be specific with this Newton's second law because I want to work in the X direction. It is accelerating in the X direction, so I'm going to use FGX in my positive X and FFK in my negative X. So that's going to be FGX minus FFK equals MAX. Okay, now, again, in the previous video, I showed you how to break this up and to determine the components FGX and FGY. I'll do a brief explanation here. So if I blow up this triangle, it's going to look like this. I've got the X component, I've got the Y component. So I've got FGY going down, I've got FGX horizontal like that, and I've got that angle theta right there, okay? And of course, I've got my FG. Oh, sorry guys, there we go. I've got my FG right here. Okay, so for my FGY, that's going to be given by the hypotenuse of the right angle triangle times cosine of theta. So mg cos theta, right? Because FG is mg. FGX is opposite to this angle, so it's going to be mg sine theta. Okay, and we're dealing with FGX right here, right now, so that's what I'm going to use. FGX is mg sine theta. Now, force of friction is given by the product between the coefficient of kinetic friction and the normal force, mu k Fn, which is equal to max. Now, to determine Fn, you have to look at your vertical forces, right? And vertical in this case means in the y direction, right? So Fn, because in the y direction, the net force is 0, the carton's not accelerating up or down, right? Okay, that means all the forces in the y direction, they have to sum to 0, okay, in terms of the magnitude. So if this one, Fn, is going up, it has certain magnitude. FGY is the only other y force, and it's going down. So it has opposite direction, but equal magnitude to Fn. So I'm going to replace Fn with FGY. And I know what FGY is. It's mg cos theta, okay? So here we go. Plug it in. Mg sine theta minus mu k mg cos theta equals max. So it's at this point in the problem, hopefully you see that there's a reason why they didn't give you the mass. It's not that it was a missing piece of information, but rather that it wasn't necessary. Because mass appears in every term and they're all addition, subtraction in between, you can cancel out mass from every term. Okay, so that gets rid of all the masses. Imagine factoring out the mass on the left. Okay, therefore you'd have one mass on the left, one mass on the right. Same idea, it cancels out. Okay, now that I've canceled out mass, I've got another similarity between these two terms, and that's the g. So I'm going to go ahead, factor out that g. Just to make the math a bit simpler, g sine theta minus mu k cos theta equals ax. And that's nice because that's what we're looking for. So everything's already been isolated. Okay, now for the next line, I'm going to write ax on the left. I'm going to write this part on the right so it looks a bit cleaner. So ax is equal to g, which is 9.8 meters per second squared. Open bracket. Okay, sine theta. Okay, so the angle's 21 degrees. Sine 21 degrees minus mu k, 0.11, times cosine of 21 degrees. And close bracket again. And when you enter this entire expression into your calculator, you are going to get ax equals 2.5 meters per second squared. Okay, and that indeed solves part A. Determine the acceleration of the carton as it slides down the plane. Okay, so there you go. There's the acceleration. Now, part B is actually rather straightforward, and it strands from kinematics. Part B says, well, if the carton starts from rest 9.25 meters up the incline, right, what's going to be the carton speed when it reaches the bottom? So a couple things, just like in any kinematics problem, when you're solving something like this, ask yourself, what do you know? Okay, so let me just sketch the incline again. I mean, you've got a box on it, and the idea is this. Okay, so it starts the incline, starts up here at v naught equals 0 meters per second, it's not moving. Okay, then we know that it's traveling 9.25 meters till it gets to the base, and that's going in the x direction because we defined, remember, x to be down the incline and y to be perpendicular to the incline. So delta x is equal to 9.25 meters. Okay, and what we're looking for is the speed here, the final speed. What we just determined, well, we just found acceleration ax to be 2.5 meters per second squared. So it's a kinematics equation. Three knowns, one unknown. We can simply plug this into a formula, one of the kinematics formulas we know, and find the answer. Okay, and that kinematics formula for part B is going to be 2a delta x equals v final squared minus v initial squared. And of course, we know v initial is 0 because it's sliding down. It starts from 0. That goes away. We're looking for v, so I'm going to go ahead and write this as v equals square root 2a delta x. Okay, square root 2, acceleration is 2.5 meters per second squared. Okay, delta x is 9.25 meters. So you see your units are going to come out to be meters squared over second squared, and then when you root that, you're going to get meters per second. Okay, so that, when you figure that out, it's going to become the square root of 46.25 meters squared per second squared, and when you finally square root that, you're going to get 6.8 meters per second. Okay, and that's all you need to figure out. It's only asking you to find the carton's speed when it reaches the bottom of the incline. So that's it, guys. I hope that was good. If it was, if you enjoyed it, be sure to click that like button and subscribe to Physics in the Flesh so you never miss a video from me. Thank you so much for watching, guys.